Hi, welcome to a new video. In this lecture, we're going to talk about artificial neural networks. So this is like one of the most popular algorithms in machine learning and AI. And they have an interesting story because if we go back in time, like in the 70s, neural networks, they were seen as a dead end. I mean, even in academia, researchers in this area, they were not getting funded because at that time there, they were lacking some methods in order to be able to use them and scale them. So again, they were not popular. But then in the like 2010, maybe a little bit earlier than that, they regained popularity because with the computational power and all the data that we had available at that time, so it was possible to show how value are these neural networks. And nowadays, I would say that they are powering the most important applications of AI and machine learning in industry, in production. So for sure, the neural networks, they are creating like most of the value, for sure. All right. So what are these artificial neural networks? So ANN, they are inspired based on neurons in our brain. So this is a simplification actually of how a neuron works. But just to give you an idea. So let's say this is a neuron. We have the cell body here. So this is where like there is a like processing of the information in the cell body, and there are what they are called dendrites, and they capture inputs, they capture information, right? And once the information is processed by the cell body, then it generates an output, and that's where we have the axon here, right? Where the information is moved to a different neuron. Again, this is a simplification, and actually in some books and some references, they say that it's not that simple like that. But every time we're creating a model, regardless it's a mathematical model, a statistical model, we know that a model is just a basic representation of real life, right? So there are some assumptions, of course. So that's why we know that the behavior is not matching 100%. But again, it's just to give you an idea on what we're trying to replicate here when we talk about neural networks. Now, this is a single neuron, but the key idea here is like simple units, even if they are basic. But when we put them together in a network, when we have multiple of these neurons, then we can analyze, we can create complex intelligence. So the idea here is that with multiple neurons, we can learn from data, right? Through training. And the whole purpose is to be able to have powerful pattern recognition. And we can use neural networks for different purposes: regression, classification, a time series analysis, in text, and in images. If we have images, we can also perform same classification operations. So every time you have complexity in terms of like the type of data, so for sure ANNs, they are the solution for that. So there is an architecture, most likely using neural networks ideas that are going to solve that problem. So let's talk about now the first like key model. So it was invented in 1957. So here we have the neuron. It was called the perceptron. This model was called the perceptron. The whole idea is that, okay, we have some inputs. So here there are three variables. Imagine you have a table, right, with three variables, three inputs, x1, x2, and x3. Then these inputs I take into the neuron that we have here. And in the neuron we have like two functions. There is always like a linear function, which we call z, and z is just the sum of the weights times the inputs or the variables plus the bias. So this is just a constant. So again, we're just these weights are parameters that we want to identify, we want to estimate. We're gonna when we train the model, we estimate these weights, right? They multiply the x. This is just like a linear function, right? So this is the sum of w weights times x, the inputs, plus the bias, right? So that's a linear function. But then on top of that, there is what we call an activation function. So the activation function is going to take z, or the result of this sum of wixi plus b, and z is going to be evaluated in the activation function. So in this example, this is a step function. In the perceptron, it's simple actually. So once you find z, if the sum of the, like the inputs times the weights plus b, if that sum is greater equal 0, then the output is going to be equal to 1. Now if it's less than that, then it's going to be equal to 0. So the perceptron was originally designed for classification purposes, for linear classification purposes, and to be more specific, for binary classification. So the output here, there are only two possible outputs, 1 or 0, right? When you use the activation function. So again, let me repeat this. First, you have a linear function here where you have the weights, which are parameters in your model, and the inputs, right? And with that information plus the bias b, then you pass that information to the activation function, and that activation function is going to generate the output of the neuron. So the single perceptron was fine for binary classification when it was possible to use a linear function to separate the classes. But even in some basic problems, the perceptron was not good to classify. So let me show you this problem, the XOR. So in this problem, it's gonna classify based on two variables, x1 and x2. So the whole idea is like if one of them, that's the OR, that's why we get the OR, right? It's if one of them, x1 or x2, are equal to 1, then the output is 1. But if both of them are equal to 0, or both of them are equal to 1, then the output is 0. That's a simple problem. But the challenge here for the perceptron is that it's not possible. It's just the way to visualize the problem. So this one, output 1, is when you have x1 equal to 0 and x2 equal to 1. And the other one is when you have x1 equal to 1 and x2 equal to 0. And the zeros are when they match, right? 0, 0 or 1, 1. So it's not possible to separate this with a single line. So you need nonlinear behaviors here to be able to classify them. Yeah? Like two lines here, that's not a single line. It's not possible to classify them with a single line. You need more than that. So at that moment, that was reported as a limited model, right? So that led to the first AI winter that I described at the beginning of the video. When I mentioned that during 20, 30 years, like starting in the 70s, the neural networks, they were seen as like a not successful algorithm. It's like it was seen like as a dead end. So that affected, of course, the evolution of this area. All right, so what was the solution? Then the solution was proposed like, let's use multi-layer perceptrons. It's like, remember the principle of stacking. So instead of having a single model, you can have, like model on top of the previous model. So instead of having like a single neuron, why not have like multiple neurons like in parallel, but also with multiple layers, right? That the stacking component. So that's gonna give like more possibilities to capture or identify more complex patterns. So in this diagram, it is a multi-layer perceptron, MLP. So we have the input layer. There is no computation here. We don't have processing here. It just passes the data. It is important to mention that these inputs, you need to scale them. So before, we get started with the training of our MLP, we need to either standardize or normalize the input variables, right? That's required. That's required. It's a common practice when you are using this type of models. Okay, so the input layers, again, it just passes the data. Then we have the hidden layers. In this example, is showing only a single hidden layer, but it's possible to have multiple layers here, like layer 1, layer 2, that's possible. You can create more complexity if you want, right? For each neuron, again, we have the same structure. Remember the linear component that has a z, right? Z equal the sum of the weights times the inputs plus b, right? So for each of these neurons, you have to compute the weights. So there are multiple parameters here in this network. Even in a simple network, there are multiple parameters. Okay, so in the hidden layers, it's gonna we're gonna learn in a hierarchical representation. So what is interpretation of this? That means, like, let's say that we're trying to analyze images, like shapes, to classify something. So in the hidden layers that are close to the input, we're gonna identify the basic stuff, lines, corners, things like that. But in the layers that are closer to the output, that's where you identify shapes, like more complex figures. So you learn hierarchical representations. So the layers that are close to the input, they are basic. They are learning like basic things, while the layers that are closer to the output, they are solving like a problem that is closer to the one that you want to solve. Just to be more specific. Now there is an output layer at the end. So the activation functions that you use here, it will depend, of course, of the type of problem that you want to solve. So let's say that you want to solve a regression problem where there is a single output. Then you just need one neuron for that. But let's say that if there is another problem where you have like a classification problem with 4 classes, then you will need 4 neurons to make that prediction. So the output layer is going to be defined by the number of outputs, but also based on the type of problem that you're solving. When we have multiple hidden layers, that's what we call like deep neural networks, right? That's when emerges the idea of deep learning, when you have like neural networks with multiple or with several hidden layers. Okay, so the power of multiple layers is now you will be able to solve like nonlinear problems, right? Including the XOR, that was an issue initially, right? The hierarchical feature learning, as I mentioned before, like in the initial layers, we capture simple patterns, edges, basic shapes. In like intermediate layers, we get intermediate patterns, textures, parts, but they are a little bit more complex than layer 1. And then layers 3 and above, we capture complex patterns, objects, concepts, until we get to the real problem that we want to solve. There is also here a universal approximation theorem that shows us like how good are these neural networks. So in this theorem, it's mentioned that a neural network with one hidden layer can approximate any continuous function. So that gives you an idea on how flexible, right, and also the complexity that you can develop using these algorithms. Okay, the activation functions. I have mentioned this before. Remember when we were every time when you see these neurons, so we have the sum that represents the weights with the inputs, right, for each neuron and the bias. But then if you see here, you see a step function in this diagram. That's the activation function. And even in the first diagram, here you have the activation function. They are really important because if you keep everything linear, I mean, if in every neuron you only have the linear component, the problem with that is like you won't be able to capture non-linearities. And on top of that, your complete network is going to collapse in a single neuron that is linear. I mean, multiple linear functions can be collapsed into a single linear function. Therefore, we need to introduce non-linearities in the neurons in order to avoid that issue. So that's why we're using the activation functions. So they help us to avoid our neural network from collapsing, right, to a single linear function. So there are different shapes And of course, different uses. I mean, you cannot use like an activation function for everything. It depends on the problem that you're solving. It also depends if it's a hidden layer or if it's an output layer. So some of the like common activation functions, we have like sigmoid. That's like, remember that the logistic regression follows this shape, values between 0 and 1, right? Probabilities, most likely. We have the hyperbolic tangent. It looks similar. It looks similar. We have ReLU. This is a popular activation function. And even the name sounds a little bit complex. The function is very simple. In the ReLU function, if you notice, this is the line. So it's not linear, but if z is negative, then the value is 0. If it's positive, it's going to be the same value. So it's just the max between 0 and z. So it's a simple function if you look at this. Now, the ReLU function it's mainly used in hidden layers, neurons that are located in hidden layers. We also have other functions like softmax. These are very important when we have like multiple classes. So again, the choice of which activation function, because you will find tables with multiple activation functions. So the way you're gonna pick them is based on what type of problem I'm solving. Regression, classification. These are not the only problems that you can solve with neural networks. Of course, we have also time series, text analytics when you're predicting text and things like that. So, but again, depending on the problem, you're gonna pick an activation function for your output neurons in the output layer, and also the position in the network is important, if it's a hidden layer or an output layer. Here, there are some guidelines, to solve simple problems. So in hidden layers, you will find that ReLU is a popular option, right? There are other alternatives here. In the output layer, it will depend, of course, on the problem. So if it's regression, so it's possible that there is no activation function at all. It's just like an identity function. It's like the same output will be, the output from the linear function will be the output of the neuron. Or if that specific regression problem, the output it's positive, then you can use ReLU. Now, if we are dealing with classification, then the output, you have two alternatives here mainly. The sigmoid, that one is a binary classification of softmax when you have multi-class, 3 or more. Now, how can you train these models, these algorithms? So let's say first that we're going to use like different packages for this. You can use scikit-learn for basic models. That's what we're going to do in this video, scikit-learn as an introduction. But when you're taking seriously, when you're developing, like a strong application, and when you're going to put something in production for sure, most likely you will use either PyTorch or, as in our book, in our textbook, they use TensorFlow. Both of them are popular. TensorFlow was developed by Google. PyTorch right now it's kept by Meta. What was Facebook before. So yeah, they maintain PyTorch and Google TensorFlow. Both of them are very capable, to develop strong models. I would say that nowadays maybe PyTorch is getting like more popularity, but again, both of them are stable solutions. All right. So how can you train the model? Even though we have these libraries with the different functions available, so just to give you an intuition on how it works. So remember that we need to, at the end, we want to find the weights, right? The weights for each neuron. We want to compute the weights of the inputs for each neuron. So and the bias, of course. So the first thing that you need to do is to initialize the weights. It cannot be like all weights equal to 0. That will create a problem. Because remember that at some point you will use like gradient descent algorithms or similar algorithms. So if everything is 0, that will cause a mess in the parameter estimation. So we need to initialize. There are several strategies for that. Like some of them are just like random strategies, or there are some more smart strategies to initialize the weights and biases in our different neurons of the different layers. So once we have initialized the parameters, then we forward pass. So that means like we provide input data and it's propagated through the whole network to make predictions. Now, what is the idea of compute this predictions with the initial parameters? The idea is to compute the error, right? To compare the prediction with the real values, with the real y values. So once we have the loss or the error, then that's why we call the algorithm backpropagation. Now we go back again, and in order to update the weights and the biases, in order to update the parameters in such a way that we start minimizing or reducing the loss or reducing the error. So that, like in every iteration, so we have this process. So when we update the weights, we keep going, and you define typically number of like maximum number of iterations, right, that you're gonna perform. Or in other frameworks, instead of iterations, they are called epochs. Epochs, same as like number of iterations. And our algorithm is gonna stop typically when either we reach the maximum number of epochs or iterations, or it's possible that at some point our model is not like improving. It's like the distance between the training error and the validation error, like it's similar, the performance. So if the gap is not closing, then it's possible that it's going to trigger our algorithm to stop. Okay, so let's go to see a couple of examples. Let me show you to you. I'm going to a notebook. You will find this notebook below this video or on Brightspace. So two examples, one for regression and one for classification. This is a problem that we have solved before in class. And I'm doing that with the intention of I don't want to like perform an EDA because you are familiar with the problem. So here in the California housing dataset, the output here, the target variable is the median value of houses. And we have 8 features, like median income in the block, the median house age, and different information, right? Okay, so in this specific case, I'm using scikit-learn because this is introduction. Again, later, we will use TensorFlow and PyTorch. In our book, they use only TensorFlow. But I will try to introduce PyTorch to give you also an idea on how it works. All right, so we load our data. We split, remember, for cross-validation, test, and training. Important, we need to scale our variables, our inputs that's required. So that's what we're doing here. Okay, and now we start training. This is a regression problem, so that's why we're using MLP regressor. Remember, MLP stands for multi-layer perceptron, and regressor because this is a classification problem. The price of the house is a numerical variable, therefore it's a regression problem. Okay, so let's see the parameters here while using hidden layer sizes. So you see two values. That means that we're defining two hidden layers. So in the first one, we have 100 neurons, and in the second one, 50. So this is a common value, right? These values are common when you are creating the layers. It's possible to add more layers if you want. The activation function, this is for the hidden layers, is ReLU. So remember, it's like 0 if z is negative, or it's going to be equal to the same value if it's positive. The solver here, the name is Adam. This is a popular solver for neural networks. It's common. It uses ideas of gradient descent. The max iter here is like maximum number of epochs. Like it's going to limit the number of times that it's going to last the training. Now here, if you notice, we have early stopping. So if at some point the model is not improving, the performance. If that happens, like in the default is 10 iterations, then the early stopping true means that it's possible that we don't reach the 500. Okay, validation fraction. So what percentage of your data you're going to use for validation. So here in this problem, the training completed in 67 iterations, less than 500. So again, that means that we activated the early stopping. So let's see the performance. Now you're familiar with this part. So you can see that in training, it was the R square was 0.8. In test, the same metric was 0.78. It's close enough. It's normal that it's a little bit lower, right? But again, it's close. You can also analyze here the mean square error, mean average error, or the root of the mean square error. Here you can see the real value with the predicted value. And this is the training loss curve. You can see how, like, after each iteration, the value of the loss. So it is expected that it's decreasing. And then after 60, remember, it stops because here it's not improving significantly. So that's why we activated the early stoppage here. Now, something that I didn't mention here, it's the number of parameters in this model. So let's say that for this problem, we use a linear regression model. I'm sorry. We use a linear regression model. So if there are only 8 input variables, then you will have like 8 betas and beta 0, like just nine parameters, right? But in this one, if you have 100 neurons in the first layer and then 50, that's going to increase the number of parameters. So for example, only for the first layer, for each neuron, you have 8 inputs. So that means that for in terms of the weights or W's, you have 8 times 100, that's 800 W's, 800 weights. And also you have the biases. So for each neuron, you have one bias, the B. So there will be 900 parameters only in the first layer. And in the, let me show you the computations here. I have them here. I have them here. Let me see. Let me open the chat. I have it here. Yeah, there you go. I have it here. Yeah. In the first one, in the hidden layer, we have 100 neurons. So it's 8 times 100, as I mentioned, plus the biases, right? So that's 900 parameters, as we mentioned. Now, in the second hidden layer, there are only 50 neurons, right? But in the previous layer, we have 900 neurons, so there is one output for each neuron, and that output is each output is an input for the next layer. That means that for each neuron here of this 50 in the second layer, there are 100 inputs. Therefore, it's increasing significantly the number of parameters, 100 times 50 plus the 50 because there are only 50 neurons. But in the first layer, there are only 900 parameters. But in the second one, we have 5,050. So it's increasing a lot. And if you keep increasing the number of neurons, of layers, you'll see that this is going to increase a lot. And in the output layer, there is only a single neuron. It's a regression problem and the bias. So this one, there are 50 inputs here. Why 50? Because in the previous layer there are 50 neurons, and each neuron is going to send an output, which is an input in the output layer. So there are only 51 parameters. So in linear regression problem, you will have only 9 parameters, but in this MLP, there are 6,000 parameters. So there is like way more complexity, right? That's why you don't use these algorithms right away. Typically, you will use them when it is required, especially for challenging problems, when there are challenging behaviors or patterns that you want to capture. But for small problems, or in general, when you have tabular data, neural networks, they are not the first option. They are all algorithms. You can call them like XGBoost for sure. It's a popular alternative these days. But again, at some point you can test, of course, neural networks if the problem is more challenging, if you have a lot of data, because to estimate this number of parameters, you need a lot of data too, right? To be able to have a good estimation of these values. All right, so the second problem is very similar, but it's for classification. So this is a wine quality dataset. There are three possibilities or three classes that we want to classify, and there are 13 features or inputs: alcohol, and like different chemical properties. Okay, so same idea. We load our data, we split our data, and remember we need to scale our data. That's really important. Uh, Always, and I need to emphasize this every time we use neural networks. Before we train the model, we need to scale our data. Okay, once we do this, we can train our model. So again, I'm using scikit-learn here. So instead of MLP regressor, here we have MLP classifier. So because this is a classification problem, we define the structure is similar, right? It's just the name of the algorithm. Then we have the hidden layers. So in the first layer, we have 64 neurons. In the second one, 32. Activation ReLU, this is popular. Same solver as in the previous one. Maximum number of iterations. In this case, we only needed 24 iterations to converge. For the early stopping was activated at that point. And this is the gap between the training accuracy and the test accuracy. One was 0.84, the other one 0.77. You can, of course, cover the details, for each class to analyze recall, precision, F1 score, to see if this result is good enough. Or, of course, you can compare with other algorithms. You can keep working, like improving the same network, like add layers or even remove some complexity if you are overfitting. That's not the case here, but if you need it, you can do that for sure. And that's it. Then you can use the model. In this case, this is a multi-class classification, right? So it's using a softmax in the output. The activation function in the output is softmax. You didn't define it, but since you're using MLP classifier, so scikit-learn is going to use softmax. So in softmax, what you get as an output is just probabilities. So for example, for the first sample one means like the first observation in the test set, the true value, the real y is class 0. The predicted one was class 0, but it gives you probabilities. So the probability that is class 0 is 0.7, probability of class 1 is 0.23, and the probability of class 2 is 0.06, which is very small, right? So class 0 was predicted because it's the one with the highest probability. So that's how it works when you use softmax, when you have a multi-class classification problem. Okay, so let's conclude this lecture just to summarize what we have learned here. So first, MLPs or multi-layer perceptrons, they help us to solve nonlinear problems. It's not just linear problems. You can solve nonlinear and challenging problems for regression, classification. Activation functions are important because they avoid that our neural network is going to collapse, and they also give us the possibility to capture nonlinearities. When you use scikit-learn, I see it more like for small models, like something very simple models. So we have MLP regressor and MLP classifier, depending on if you are doing regression or classification. But again, for more challenging problems and in real life, we will use more TensorFlow, PyTorch. These two are the leading libraries when we are using regression models, when we're using neural networks. So starting our next video, we're going to start using those libraries. Always remember to scale your data, because the neural networks are sensitive, to these values when they are different. that's going to affect the training. So it's important. And of course, just to complete this presentation, remember that these algorithms are really powerful in real life. Like when there is a challenge problem in AI, typically it's going to be solved by a neural network. Like there are different architectures that we will go over some of the other architectures in the upcoming videos. All right, that's everything for today. I'll see you in our next video.